Section 24.5 Predicting Molecular Structure Using Qualitative Molecular Orbital Theory. Molecular orbitals are simply mathematical functions that are used to construct the determinantal wave function of a multi-electron molecule. Molecular orbitals may not have any physical meaning. Now let's talk about the canonical MO theory. Canonical MO theory is delocalized bonding model. It's also called symmetry-adapted MO theory. The symmetry-adapted canonical molecular orbitals are delocalized over the whole molecule. They form the basis for an irreducible representation of the point group defined by the symmetry of the molecule. So if you learned group theory, you know water has a C2V symmetry, or you may say water belongs to the C2V point group. In the C2V point group, there are 4 different symmetry operations. Number 1, doing nothing. It corresponds to the identity symmetry element. Number 2, rotation. So the water molecule can rotate about the principal C2 axis 180 degrees. Number 3, reflection. Reflection about a sigma V symmetry plane that's perpendicular to the water molecule. Number 4, another reflection with respect to a different sigma V symmetry plane that contains the water molecule. So again, we have 4 symmetry operations in this C2V point group. This C2V point group contains 4 irreducible representations: A1, A2, B1, B2. So A means this MO here, for example, is symmetric with respect to the rotation about the C2 axis. B means anti-symmetric after the rotation. This 1 in the subscript means this MO is symmetric with respect to the symmetry plane that's perpendicular to the water molecule. And 2 means anti-symmetric with respect to the refraction. So now let's look at this A1 symmetry. So this MO has the A1 symmetry, or A1 irreducible representation. That means this MO is totally symmetric with respect to the rotation and reflection, with respect to the symmetry plane that's perpendicular to the water molecule. B2 means it's anti-symmetric after rotation, anti-symmetric after reflection. So you can imagine this C2 axis here, and then if you rotate this MO 180 degrees, well, the sign changes. The plus sign goes here, the minus sign goes here. So it's anti-symmetric with respect to rotation. Therefore, you see this letter B here. What about this 2? 2 means anti-symmetric with respect to the symmetry plane that's perpendicular to the water molecule. So again, imagine a symmetry plane here, perpendicular to the water molecule. After the reflection, the plus sign goes here, the minus sign goes here. Therefore, this is a B2 symmetry. This one is also completely symmetric with respect to rotation and reflection. So it's also a A1 symmetry. But we have the first A1 here, so you have 1 A1, 2 A1. And this is our first B2, so it's 1 B2. Finally, there's a B1 symmetry. B1 means if you rotate this, the sign changes. But if you do a reflection with respect to the symmetry plane that's perpendicular to water, there's no sign change. Therefore, it's B1. In this 4 MOs, we have 2 electrons here, 2 electrons here, 2 electrons here, and 2 electrons here. A total of 8 electrons occupy these 4 MOs. So this one is our HOMO. And clearly, this orbital, centered on oxygen, does not interact with the hydrogen atoms. So this can be interpreted as the lone pair electrons. But if you learned general chemistry, you know water has 4 lone pair electrons, not just 2. So where are the other 2 lone pair electrons? Well, some here. Okay? Some here. The top half of this 2s orbital, centered on the oxygen atom, is the lone pair electron. So a little bit here, a little bit here. And if you split this p orbitals, okay, the top half is more like the lone pair electrons as well. So you have 2 lone pair electrons here, and a little bit here, a little bit here, a little bit here. So together you have 4 lone pair electrons. And similarly, if you compare the localized MO theory versus this canonical MO theory, you can somehow relate the number of sigma bonds in the localized MO theory to these 3 bonding orbitals. So you can see there are 3 bonding orbitals, but it doesn't mean there are 3 bonds. We can argue that, well, this is not a entirely bonding orbital. Again, the bottom half of this 2s orbital interact with these 2 1s orbitals. So it's not entirely 100% bonding orbital. So part of it is lone pair, part of it is bonding orbital. Same here. So not 100% bonding, not 100% bonding. So together, this one, this one, this one together, you have 4 bonding electrons and 2 lone pair electrons.